Welcome back to General Statistics. In our next unit, we're going to explore understanding chance processes, and ultimately we'll be building into a better understanding of sampling and how samples relate to populations. We need to understand this topic really well so that we can look in our final unit at different ways to draw inferences about a population based on a sample. But before we can get to that point, it's important for you to understand how it's possible to even draw inferences about a population from a sample before we can move into picking which type of inference you can draw. So that's why in this chapter on the law, why we start out chance variability by looking at the law of averages before we get into the standard error and the expected value. Okay. First, we need to understand that chance processes in general. So in short, any sample average is a random variable. This is a really difficult, a big idea to take in. So we're going to break it down into some simple examples using box models, which we'll figure out how to set up in this session. But to give you a general idea of the underlying issue here, let's say you took a sample and you compute an average. That's a number, but if you did it all again, it would have come out a bit differently. And in fact, each time you do it again, it would come out a little bit differently. And this is a key aspect of a random variable, or as we will frame, a chance process. So let's examine the law of averages. The law of averages is just an idea that helps us to conceptualize thinking about averages and random variability or chance error. So let's say you draw some tickets at random from a box and take the average of the numbers you get. This will be close to the average of all the numbers in the box, but it will be a little bit off. That amount that it's off is the chance error. And as you can see, there's chance error in drawing numbers from a box and thinking about the tosses of a coin. And the error is likely to be large in absolute terms, but small relative to the number of tosses. And let's unpack this a little bit. So we have two figures here. In the first one, I'm sure you recall, there is a fun discussion between Carrick and his assistant about his deriving the chance error idea and thinking about the law of averages. And in his experiment, he tosses the coin 10,000 times while he's imprisoned. Or detained. And you can see that on the x-axis, there's 10,000 tosses here. He really did toss the coin 10,000 times. And then on the y-axis, we have the number of heads minus half the number of tosses. Why does this make sense? Well, let's keep looking here. The difference is plotted against the number of tosses. So this helps us get a difference between an expected value and an actual value. And this is an idea we're going to look at in several different contexts coming up. the idea that there's an expected value and an observed value. So you can see on figure 1, as the number of tosses goes up, the absolute size of the chance error also tends to go up. See here on the left, we've got the absolute size. Of course, this makes sense because as you have more tosses, there's more actual trials. We can see that in figure 2, though, the chance error is expressed as a percentage of the number of tosses. And so when the number of tosses goes up, see we're going along, the percentage goes down. And you do see some variability here in the beginning. That's kind of the point. When there's a smaller number of tosses, there's a higher percent of variability. And as you complete an increasingly more tosses, the chance error gets smaller. And this is such an important point. Why is this going to be so important to us in the long run? Because we are going to think about how later on, how sample size is really instrumental in our calculations to draw inferences about if there was a difference or an effect on our sample and if we can relate it to our population. So we'll see as we're going that the number of trials, the number of instances, the number of participants, in this case, the number of tosses, that as you have an increasingly high number of tosses or sample size, you're going to see a relative smaller chance error. And we can relate this already to some ideas that we've discussed when we were thinking about the power of the GSS data set, which is a population level data set. And what in part makes it so powerful is that it represents the population and also has a very high number of participants. We wouldn't expect the GSS data set to be anywhere near as powerful. And I'm sure you can see this intuitively if it was just 10 participants randomly selected from across the US, as opposed to the 10,000 per wave. And so I'm sure you can sort of intuitively already see, of course, it makes sense. We need to get a big sample to really represent the variation, but once we start getting to an optimal sample size, then we've represented the range of variation and the chance error is going down more and more. And we're going to revisit this idea more than once. So if it doesn't quite jive with you yet, don't worry. We'll come back to this idea a few more times. So I just pulled out a couple of problems here. This first one, the machine has been designed to toss a coin automatically and keep track of the number of heads. After 1,000 tosses, it has 550 heads. Let's find the chance error in absolute terms and as a percentage. So just to make sure we can see this working out, we have a total number of 10,000 tosses. Or excuse me, 1,000 tosses. I was thinking about this part. Remember that the chance error, the number of heads, is equal to half the number of tosses plus chance error. Okay, and we can shuffle this around to think about how we can get our chance error from our having just the number of heads. So we'll have, if we have 1,000 tosses and 550 heads, one half of the number of tosses is, we have 550 heads. One half the number of tosses is 500 plus chance error. I'm sure you can see that our chance error is 50. That's our absolute. Chance error. We also need to represent it as the percentage of the number of tosses, and that's a much more accurate way to present the chance error. In that case, we know that we already know that the chance error is 50, but to make it a percentage, we need to put our 50 over the number of tosses. We would just take 50 out of our total number of tosses, which is 1,000, and we end up with a 5% chance error. Does that make sense? Okay, and our next, okay. In the next bit, we're going to consider some different scenarios. And just think through, how do we get these, which one is better? Oops. The coin is tossed and you win $1 if there are more than 60% heads. Is it better to do 10 tosses or 100? In this case, it's better to do 10 tosses, yes, because we want to get more than 60 heads, more than 60% heads. That's a rather extreme score, so we're going to be more likely to have a more extreme rate if we have a smaller number of tosses. Same scenario, but you now win $1 if there are more than 40% heads. So now we just want it to be more than 40%. And we want the 100. That's right. 100 tosses would be a better choice here in B. Because now the chance variability hurts you because we want more than 40% heads. So we don't want an extreme score. Now we win the $1 in part C if there's between 40 and 60% heads. It's again going to be better to go with 100 in this case because the smaller amount of error would be on your side. And if we look at our final example, you win the $1 if there are exactly 50% heads. We're going to want to go with 10 exactly because we're going to be more likely to get exactly 50% when we have a smaller number of tosses. As the number of tosses goes up, there's a decreasing probability for the number of heads to be exactly equal to the expected number. It just has to do with the total possible values. So next we discuss a chance process. Another way to think about a chance process is that it's a random process. And it's very important to remember that the law of averages does not work by changing chances. The odds and you can think back to our item on the exam where there was 10 given 9 tosses were heads. What's the chance of having a 10th head? Well, after a run of heads, a head is just as likely as a tail. It does not matter. They're completely independent. The chances don't change. It just has to do with the difference between the expected and observed values, which are terms, of course, we haven't fully unpacked. We'll really look at that in more depth later. But the real take-home message here is that a chance process comes out differently each time. So remember, you could get an average of we'll talk a lot about box models, but we could apply this to more complex ideas as well. The reason that we are starting with these simpler models that relate to games and give us some nice clear-cut outcomes are that it's much harder to start out with thinking through these in the context of complex research questions. It's important to think about what extent, the extent to which the numbers are influenced by chance. We face this question over and over in statistics, and a chance process is instrumental in many of our calculations and assumptions that underlie all sorts of statistical procedures. This you've already been thinking about it, but you may not realize it because we've been talking about random sampling. Random sampling itself is a chance process. You get by chance the random assortment of people from your population that you've sampled. If you took another random sample again, you would get a different random assortment of people, and your sample average would come out a little differently each time. This is the characteristic of a random process. So there's 2 important ideas behind the general strategy we're working with here. First, we're using these games as an analogy between the process we're studying, sampling, which is the underlying idea here, the underlying randomness and sampling. And we're just using these games, tickets from a box, for example, as a analogy. And once you really get a good grasp on it, it'll make it a lot easier down the road to understand the ideas that we'll discuss about the more refined issues in sampling. And we'll also work to connect the variability that you want to know about with the chance variability in the sum of numbers from a box. We use the sum of the numbers because it's just a representative of a chance variability. The point is that the chance variability in the sum of numbers drawn from a box is easy to analyze mathematically. So we can understand these issues without getting into some of the trickier mathematics that might confuse the things. So let's think about this idea of the sum of draws. Now, this is just a conceptual idea that's going to help us get to some more complicated ideas. And it helps us to simplify the complicated process for generating a number and modeling it on drawing numbers from a box. You can see we use a sample box that has 6 tickets with numbers 1 through 6. They resemble a die, so you could think about it as a dice problem if that resonates more with you. The point to remember, an important point to remember, is that in the box model that we are generally discussing, the idea would be that it's a with replacement sort of model to refer back to some of the ideas from our previous brief discussion of probability. So the sum of draws is a subject to chance variability. If the draw turns out one way, the sum is one thing. If they turn out differently, the sum is different too. It's random. For example, if you draw twice from at random, again with replacement, and you add up the numbers, your first draw might be 4 and the second might be 6, and then the sum would be 10, or the first draw might be 2 and the second is 5, so the sum would be 7. There's so many possibilities. I'm sure you can imagine, you've all played board games before. This is why we're starting with this simple model. So it's random how it comes out. You know that. And this idea of randomness in the chance process, and then because the sum of draws is a direct result of the chance process, the sum of draws is a statistic we're calculating based on a chance process, it's also a random variable. And I know that this idea can take a while to sink in, so just let it keep percolating on that idea over the next few chapters, that the sum of draws or the sample average, these are considered random variables. And we will unpack that idea more. And as in our next step, we're going to look at constructing a box model, and the sum of draws being our major statistic of consideration. So when we make a box model, we have 3 basic questions. Which numbers go into the box? How many of each kind of number? And how many draws? See, we can arrange this any way that works. As we just looked at, we could arrange it so that 6 numbers go into the box, like a dice, or a die, excuse me. And then there'd be 1 number of each kind, and the number of draws is just equal to however many trials you conduct. The box model gives us draws made at random from a box of tickets, and this is a great example of chance variability. When we look at this in the context of gaming processes, which later will translate into sampling processes, we can examine our sum of draws statistic, and just the real benefit to using our simple box model is that it gives us a model that works for lots of processes rather than another approach which would just give us a lot of special exceptions, which is harder to deal with. So hopefully, I guess, you've gambled before. If not, there's a standard layout here. This is a layout for a standard roulette table, and they use roulette as an example throughout the box model section in setting it up. And roulette is very interesting to statisticians generally because it is such a great probability problem. So you can see that roulette basically has 38, you may not be able to see that, but there's 38 possible outcomes. There you can bet on any of the 36 different numbers, or red and black. It's also possible to do some of these other odds, other bets rather, where you bet on the first 12, the second 12, or the third 12. That's a different type of bet. We're looking at some of the more standard bets. And how is that different? Well, generally speaking, if you go play roulette, there will be different rules. There's slightly different rules for the size of bet you have to lay down on some of these. So that's what makes it different. It changes the probabilities, whereas all of these single numbers pay 35 to 1. So it's great odds if you can get it. So let's say you play roulette many times. You play the first time and the you do one play. So you bet $1 on red each time. So how we'll start to unpack it. Just thinking about how there's red or black outcomes. Red or black pays even money. So you can put your whole bet on red or your whole bet on black. Arguably, it's the best way to play roulette if you're going to. I'd amend that a little bit slightly, but not right now because I don't want to confuse things. So if you put your bet on red or black, you have a 50% chance of, well, not quite, but say you bet $1 on red each time. By the end of, let's say, 10 trials, you end up ahead or behind by some amount, depending on how the ball landed each time. It's a completely random process. The ball falls totally randomly each time, much to the chagrin of gamblers. And that difference, the amount of difference, is your net gain. Would you expect your net gain to be net gain, the absolute value of your net gain, remembering that an absolute value removes a negative, to be higher for 10 trials or 100 trials? Well, this idea goes back to what we were just discussing earlier, which is this chance error. So yeah, if your net gain is more likely to have a higher absolute value for 10 trials than 100, the more you keep playing, the more likely you are to end up at even amount ahead or behind. And so that can be good if you want to take advantage of that in a gambling scenario. You want to, you know, do a small number of bets and stop while you're ahead. You know, that's the key thing that tricks people up when they're gambling. In gambling problems in which the same bet is made several times, you can set up your box model to show the amount that can be won or lost on each play, the chance of drawing any particular value of the box equal to the chance of winning that amount on a single play, and the number of draws is equal to the number of plays. So we'll see later, number of draws or plays is similar to the idea of the number of participants. And if we just to preview how we'll map this onto sampling, is to remember that your chance of drawing, if you, let's say you have a whole population available to you and every person is equally available, then the chance of drawing any particular type of person of interest from your population is random. You might be able to predict it, or we deal with this in sampling strategies in different ways to try to stratify our populations to be representative, because based on possible confounding variables. But I don't want to break it to get too much into the complexities of survey sampling yet. I'm just having you think ahead about how we are not just talking about gambling. We're just using gambling to help us think through really complex issues in survey sampling. And gambling is, a fun way to think about these odds. In a normal semester, we have more time to do some actual activities, with real objects like dice. But you can certainly, in your copious free time, illustrate lots of these points about a box model that we just discussed, just even using a simple dice model. You don't have to go play roulette. You can just get some dice and look at how the distribution of particular scores of interests, or if you use a dice, you could look at the chances of even and odds or the occurrence of them. I understand how much free time we all have. That's why we're not doing that fun activity right now. But should you find yourself eager for a little break, there you go. May the odds be ever in your favor.